All right, so this is lesson 2 of our differential equations unit. And in this lesson, we are going to talk about Euler's method. His name is pronounced like that word right there. E-U-L-E-R is Leonhard Euler. He's a German, and his name is pronounced Euler. Not Euler, Euler. And if there ever was a litmus test for a real mathematician versus somebody who's faking it, it would be, hey, read this name. And if someone says Euler, you get to laugh at them and say, you obviously did not have Mrs. Bibber because his name is Euler. Okay, soapbox done. So, Euler's method is really what I like to call numerical slope fields. When we had slope fields before, we had all these little lines that tell us where to go and how much to increase and kind of how much to decrease, and we could draw in a solution curve to a differential equation. What Euler's method lets us do is it lets us take a differential equation, and given some initial condition, we can find later values. So if I know that like the point 1, 2 was on a solution, and I want to know, well, what's the y value going to be when x equals, 2, we could use Euler's method to do that. So Euler's method has a bunch of steps, and I am going to talk about them right now. So when we do Euler's method, we're actually going to use a chart, and we're going to have 3 columns on our chart. We're going to have x, y, and then delta y equals a dy dx times a delta x. And what that's going to allow us to do is it's going to say x and y are our initial conditions, and then y is going to change in each row by taking the derivative and multiplying by the change in x. So row 1 is your initial condition. Row 2 and 3 should each increase or decrease by a delta x. That'll be given to you. It will then increase and decrease also by the delta y that you calculate. And then you continue on and on. So what does all that mean? What does it look like? Well, here we go. Here's a differential equation. Dy dx equals xy squared. And there's a solution for that contains the point 2, 3. So some particular solution to that differential equation contains the point 2, 3. So first thing I ask, though, here is find the line tangent to the solution curve at the point 2, 3, and use the tangent line to estimate the y value when x equals 2.05. So, tangent lines come up all the time. To get a tangent line, you need an x, you need a y, and then you need a slope. So my slope is going to come from dy dx. Dy dx here, pardon me, is going to be the derivative. Well, that derivative is implicit. So it's xy squared. I'm going to evaluate that at the point 2, 3. So I'm going to get 2 times 3 squared, which is 18. So my tangent line is y minus y1 equals mx minus x1. And we're supposed to use that tangent line to approximate x equals 2.05. So y minus 3 equals 18 times 2.05 minus 2. Y minus 3 equals 18 times 0.05. Y equals 18 times 0.05 plus 3. And maybe you're thinking, Mrs. Weber, why can't we just do this all in one step? Well, because this is what sets up how Euler's method works. To get the new y value, we take the old y value and then add the derivative times the change in x. This is like y0, and this is the derivative, and that's delta x. So dy dx times delta x gives you delta y. All right, so enough of that. So 18 times 0.05 plus 3. So 18 times 0.05 plus 3 gives me 3.9. So the new point is 2.05, 3.9. What we just did there is we use a tangent line to approximate a value near the point of tangency. And that's all fine and good, and the tangent lines are usually decent approximators as long as you're close to your point of tangency. Euler's method takes that one step further and says instead of going directly from 2 to 2.05, let's go up by 0.01 each time and estimate values that way. So here's the way it works. We will have Euler's method, which means set up a chart, x, y, and then delta y equals dy dx times delta x, which in this case is going to be xy squared times 0.01. My first point is the point 2, 3. Delta y is 2 times 3 squared times 0.01, which is 18 times 0.01, which is 0.18. So now x goes up by delta x, y goes up by this amount, and then you do it again. So the new delta y is the new x times the new y squared times 0.01, 2.01 and 3.18, 2.01 times 3.18 squared times 0.01 is 0.203 something. So I have now 2.02 and then 3.383 something. So then my new delta y is 2.02 times 3.383 squared times 0.01. So I'm going to have 2.02 times, this was 3.18 plus the value above it squared times 0.01. What was that again? 0.2312. So then I have 2.03. Now, I'm going to do this next part because you don't have to keep watching me doing this to get us all the way down to 2.05. So I'm going to pause this and do the next part. You should definitely be doing it on your own and making sure you come up with the same thing. All right, so I'm down to the last row. I did 2.03 and got 0.265. 2.04 had a y value of 3.879. I plugged that in, I got 307. Now I'm on the row of 2.05. When you get to the last row, and you know you're at the last row, you do not have to do delta y because we're about to stop. It said estimate 2.05. So at 2.05, my new y value is the 3.879 plus the 307. And I get 4.186. And there we go. So that is what we have. Notice that the Euler's method calculation is a little bit higher, but still close to the tangent line. And I don't want to spend the time to do this right now. If I were to take the second derivative of this, you would find that the curve is concave up at this point, which means the tangent line is an under approximation anyway. So this is likely closer to the actual value than the tangent line approximation was. So, long story short, Euler's method is really easy, just quite tedious, because you just have to go through as many rows as it tells you to go through. X, y, and then delta y equals x and y plugged into the derivative times the delta x that you're given. So we're going to do one more with just 3 steps. Solution curve for this derivative contains the point 2, -5. Estimate the y value when x is 1.4 using Euler's method in 3 steps. So I'm starting at 2. I want to go backwards to 1.04. That's backwards -0.6 basically. So when I use 3 steps, my delta x is going to be -0.2. So x, y, delta y equals dy dx times a -0.2. And then we're just going to write it out. So I'm going to just sit here and quietly write it. Follow along as you do it in your own calculator, but basically I'm just going to be plugging things in. So I got negative 4.788. It's just tedious. You do it right on the screen, and that's it. That is all there is to Euler's method. So again, what's really going on is that we have some kind of a slope field, and we have a solution curve, and we want to use that solution curve to move forward a little bit more. So if you want to see a picture of what's really going on, if you have a slope field, let's say I have this one, and I know that this point is in the slope field, I can use Euler's method to say, well, where do I go next? Well, I go to here. Then where do I go next? I go to here. Where do I go next? Then I go to here. And Euler's method will tell me specifically how to move through that slope field in a better way than me just kind of winging it. All right, so that's all we've got for this. The terrible joke of the day is, how do you get a tissue to dance? You put a little boogie in it. All right, we're all done.